Can I ask you, for clarification, please?
Yeah.
So we can place our
Oh, yeah. If people want to ask something, yeah, of course. Okay.
I would think that everyone will agree on that, but myself have discovered that on certain specific topics I do not like it because I'm like, just wait, I'll get to it.
Right.
This is because, especially if it is like something more prepared, like something more fixed, it's like, well, just wait.
Yeah, I'm
will
gonna
see.
get there.
I'm gonna get there. Please,
Yeah, yes.
just don't interrupt me because I will lose it.
Yes,
Yeah.
no, that's true.
So.
No, but it's okay. Of course, if it's a substantive question, we may leave to the end. But I would like to have more time for discussion rather than cramming a lot of things. So we're going to go over a few things, and then we open up.
Perfect.
So thank you everybody for joining the workshop, for coming from so far away. And it is a pleasure for me to have been organizing this and to have these amazing keynote speakers for a day and a half workshop is a pleasure for us. And of course it is a pleasure for us to have Otávio as the first keynote. As you already know, the workshop is going to last 1 day and a half. Today is the full day. We end up finishing around 6:10 or 6:20 in the afternoon, and tomorrow we start at 10, but we finish at 2 p.m. And so I'm going to leave you for the first session with Gabriel and Otávio. Thank you very much.
Thank you, Maria. So we will have, or most of you know Otávio from the University of Miami. He will be speaking for about 40-45 minutes. If you've got small questions to clarify, you can raise your hand. And if it is something more substantial, we can leave it to the end. He will focus on leaving some room for the discussion. So it begins.
All right. Well, first of all, I'd like to thank Maria for the lovely invitation to return to UNAM. It's always a pleasure to come back to Mexico City, a city that I always enjoy. And of course to the whole group here at UNAM and all the other speakers as well. This is a very interesting workshop, right? So we'll be exploring different sides of defectiveness in the sciences. So in a way, it's odd that I'll start with something that I actually don't think is a defectiveness, right? Incompleteness in the science. That's actually what I'll be trying to argue for. But it is something that is perceived to be so. Right? So what I'll be doing in this talk is to try to identify certain different kinds of incompleteness In each case, I discuss why is it that it may be perceived to be some form of defectiveness, and why, in fact, it's not, right? So of course, it's a huge topic. There's a lot to be said. I'm going to just focus on 3 specific points, give some examples to illustrate them, and then we'll open up for discussion. Now, of course, there are a number of features in the sciences that we want to make sure all things being considered that are there, right? Accuracy, empirical support, relevance are all good features that scientific theories and traits of scientific practice, ideally at least, should preserve, right? And the question is whether completeness is among those, right? And so I think actually there is a significant gap between what is ideal to be the case and what's actually the case as far as science is concerned, right? And for a number of reasons, in fact, often scientific theories are empirically inaccurate, empirically unsupported, or often even irrelevant. But they're not meant to be so, right? Again, as with everything in science, which is also very complicated, even those things sometimes are meant to be so. So, for example, if you consider some climate models, some of them are deliberately empirically inadequate, but they are good enough for practical purposes, right? So, for example, trying to predict some paths of hurricanes, right? And the models may be very generic and gross in terms of the way in which the amount of information that they encode about certain regions in a map, right? So, and you know that they're going to be empirically inadequate, right? They're not fine-grained enough, right? But it'll be too costly, too complicated to get exactly the sharp, specific, accurate information, where the general trend is good enough, right? So in those cases, for pragmatic purposes, you may just live with an empirically inadequate model, right? Of course, there's empirical inadequacy and empirical inadequacy, right? If it's so far off, the model will be just useless, right? But it can be empirically inadequate, but it's still good enough, right? So even though we aim for empirically adequate theories, well, sometimes even empirically inadequate might be good enough. Right? So, and despite that, of course, I still think that it makes sense to search for other things being equal. Search for empirically adequate models, informative models, accurate models, right? And of course, relevant ones. Now, and I think the case for completeness is different, right? We may have the idea of, well, it would be very nice if we could have complete information about a certain scientific domain, right? That would be, of course, good if you can get it, right? The question is, first, can we get it, right? And secondly, is it worthwhile trying to get it, right? How far should we be willing to go into the business of trying to reach for completeness, right? In one of the cases I'm going to consider, we have obviously trade-offs, right? So we may be able to get complete information about certain things, provided the information is also inconsistent, right? Is that a trade-off you're willing to do? At what price are you willing to have completeness, right? Because maybe if that's a goal, other traits may need to be left along the way, right? And so that's some of the issues that need to be taken into account, right? So, of course, several of you know I have no problems with inconsistent bits of information, provided they are not trivial, right? Provided that not everything follows from that, right? So you can still live with an incomplete scientific or mathematical theory, provided that not everything follows from it. So in some cases, you naturally may be interested to explore how far you can push the completeness. But there is always a trade-off, and that's one of the things that I'll be trying to do, right? So then you need to think about how far you're willing to go in requiring completeness as an ideal goal for scientific practice. Okay, so I'll try to argue that this incompleteness is actually not just accidental, it's ubiquitous, right? You find all over the place in the sciences, in mathematics, from empirical domains. And I think it is indeed a crucial salient feature of scientific practice. And it's something that we can learn interesting lessons by taking it seriously. Okay, so I'm going to examine the key role that incompleteness play in several pieces of scientific reasoning, right? And try to make sense of ways of accommodating that incompleteness. So first, I think there are at least 3 kinds of incompleteness. Certainly there are more, but at least for today, I'm going to focus on these 3, right? So first, of course, we have inferential incompleteness. Right? Incompleteness about what can be inferred about a certain domain of objects. Right? And then inferential, of course, if you're talking about inference, it depends on the kind of logic you're using, the features of the language you're going to be used in order to get it. And here, of course, there's a lot of well-known information about the sources and features of that kind of incompleteness, right? Certain things that cannot be proved given other assumptions and given a logic. I'm going to illustrate this again with examples from mathematics all the way to physics and economics. So it's something that it's actually wide-ranging, this form of inferential incompleteness. But also we have, let's try to draw a line between that and information incompleteness, right? Of course, you may always think that inferential incompleteness provides a form of informational incompleteness in the sense that certain bits of information may not be derivable from other things in light of inferential incompleteness, right? So in that sense, okay, you can think of informational incompleteness as being a broader category, right? But what I have in mind here is information as dealing with partiality of data, right? Partiality of information about specific bits of the domain, whether you're inferring certain things or not, right? This is just part of the collection procedures you may get to obtain information about a domain or not. So in that sense, it's different from inferential. So it's a different source of incompleteness. And finally, we have semantic incompleteness. Again, you may say, look, information can be cast semantically, right? So maybe semantic information is the most basic category here, right? And so the idea here is, this is a form of incompleteness that it's tied directly to the referential devices of certain languages, right? The tools in order for you to refer to certain things and try to specify the content of what's being said. As you can see, I'm not suggesting that there is a sharp boundary, right, between these kinds of incompleteness. So in a way, these very distinctions are vague, right? So there are, I think there are clear cases of, things that fall under semantic incompleteness and may not fall, obviously, in inferential completeness and so on. So it's a vague distinction, but a vague distinction is still a distinction, right? And that's important, right? And that's what I'm trying to suggest. I think there are those, even though the distinctions here are vague, they're still marking different sources of incompleteness, right? One is primarily, the first one primarily an inferential one, so it's tied to some logical machinery. The second one is primarily related to pieces of data about the domain, and the third about meanings and referential devices of language. So in that sense, they are distinct, right, even though they are obviously connected. So let me say a little bit about each of these three things and why they matter and why they are inevitable. Right? Okay. So first, with inferential completeness, of course, the main source of these kinds of incompleteness we're all familiar with will come from Gödel's incompleteness theorem, right? So if you consider the first theorem, if you have a theory, a consistent theory, powerful enough to express arithmetical notions in it, then you can prove that's Gödel's result that there is a sentence in the language of that theory, an arithmetical sentence in the language of the theory, that it's true, recognizably true, but that cannot be proved from the principles of the theory. Right? So it's actually a beautiful proof that Gödel came up. Right? The reason why you need to have enough expressive resources to have arithmetic in it is that so that you can construct this sentence. Right? What this sentence says is, it says of itself roughly, I cannot be proved. Right? So now, that is an arithmetical sentence in the sense that what Gödel devised was a procedure to associate to each symbol of the language one and only one number, then strings of symbols and formulas in the language will have one unique number, right? And so that if you think of proof as a sequence of sentences in the language, given that each sentence has a unique number, a proof will have one unique number. Right? So to say that this sentence is not provable means that there is no number that is a unique Gödel number for the proof of that sentence. Right? So, and when you establish that, if the sentence is true, that would mean that there's something that cannot be proved, right? But that means that the system is then incomplete, right? It's crucial that this system be consistent, because if it were inconsistent, well, then you could prove including that sentence, right? So it's a clear assumption of the Gödel result that you get a consistent theory powerful enough to get arithmetic. Now, this result has an obvious and important consequence. That's the Gödel's second incompleteness theorem, right? Based on the similar assumptions of the original one. The very notion of consistency, right? That you cannot prove something from the system is one sense of consistency is that something cannot be proved in the system. You cannot prove formulas of certain sorts in that system. So the very notion of consistency becomes an arithmetical notion. So that very notion can be used to express a corresponding Gödelian sentence that says that the consistency of the theory itself cannot be proved if the theory is indeed consistent. Right? And that's the second incompleteness result. Now, when Gödel proved that result, it came as a big surprise. Right? People thought that, well, we have the axioms of piano arithmetic, we should be able to prove everything that needs to be proved about piano arithmetic out of these axioms. Right? And there was a kind of an assumption that kind of part of the motivation to axiomatize theories was to try to get complete, you have some system of axioms from which you can derive everything that can be proved about the system. So Gödel showed that that's not right, assuming, well, the consistency of the theory, assuming some expressive resources in the language. We're going to return to that in a moment, right? But it was a surprise, right? And that came primarily from the content itself of the very notions that we are considering. Right? The very content of those arithmetical notions are such that they lead one to create a Gödel sentence. Right? That's going to be true, but cannot be proved. Right? Plus, of course, the logic that it's being used. Now, one interesting trait that this kind of inferential incompleteness brings about is that there is something about our understanding of arithmetical notions that seems to be prior to any axiomatization of arithmetic, right? In fact, I think that's one of the interesting philosophical results of Gödel's theorem, right? That show, because we do understand the truth of the Gödelian sentence, right? It's actually true in arithmetic that that sentence cannot be proved, and we understand that not on the basis of anything given by the axioms, because the truth of that sentence can be determined independently of the axioms. In fact, the axioms are such that you cannot derive the truth of the sentence from them. You can always say, all right, we're going to add that sentence as a new axiom of arithmetic, right? But of course, that doesn't go very far. You create a new Gödelian sentence out of that one, so you haven't gained anything, right? And I think that's an interesting reminder, right, that of an important limit of axiomatization. Axiomatization are extremely important. There's no doubt about that. They illuminate a number of traits of a certain domain, but also they can distort, they can introduce artificial distinctions, and can derail certain fields in some ways, right? So one reminder here is that the kind of incompleteness that Gödel identified, I think it's significant because it's a reminder about the boundaries of what we can understand conceptually, and the role that axiomatization plays in that, right? And the limited role that axiomatization plays. Now, this is a point that I think Michael Dummett in an earlier discussion highlighted. So he says, in an attempt to characterize the totality of natural numbers, for example, for the purpose of pointing out that any model over a formal system in which U, a particular Gödel sentence for the system, is false, will contain elements not in this totality. So if you're attempting to trying to characterize the totality of these numbers, right? You say, oh, look, this Gödel sentence, maybe it will be false, right? But to show that it's false, you need to invoke something that it's not in the system in question, right? So to do that, you need to express things like, use expressions such as set or finitely often. And he continues, if we then try to give an account of the meaning of this expression, set or finitely often, by means of a stipulation of the assertions we wish to make involving it, this account could in turn be embodied in a formal system within which a definition of natural number could be given. So you may say, oh, okay, I'm going to try to characterize this totality, right? And when I try to do that, I realize that I need to refer to things like set or finitely often, right? When I do that, what turns out is I'm now open to a re-axiomatization of the claims I've just made involving these notions of set or finitely often. And then what happens? Well, the very notion of natural number that I'm trying to pinpoint will be open to a new Gödelian result, right? In view of the fact that Gödel's theorem applies to any system which contains arithmetic, there would again be an arithmetical statement expressible but not provable in the system, which we could recognize to be true. We should thus not have succeeded by these means in giving a complete characterization of the concept natural number. So one of the lessons here, at least one philosophical lesson, and then of course Dummett then go on to take present his own take on these matters. But one of the lessons that is presented here is the reminder, right, about the limits of axiomatization, right? If you have something that is expressive enough to include arithmetic in it. I think this is an important lesson, an important reminder of the significance of incompleteness, right? There's something about the concepts we're dealing, arithmetical concepts, and then the same goes if you extend beyond just theoretical concepts and other mathematical concepts that go beyond arithmetic, that you cannot pinpoint these concepts with a bunch of axioms. Okay, so one of the questions here is what will happen, right? There's this insight that Demet presented, right? Can we extend that to things that go beyond arithmetic, right? How much of the concepts that we use, provided that they include arithmetical concepts, right? How much of that will be such that we replicate and find additional incompleteness in them, right? In other words, is our understanding of the relevant concepts in these cases not fully characterized by the relevant axioms, right? Because here's a very a view about mathematics that actually is very endearing. Mathematics studies some domains, and this domain is introduced by specifying some axioms. Once the axioms is specified, well, whatever follows from them, there you go. That's your domain of mathematics, right? And a lot of mathematics is done in that way. It's just that you have to understand that if the domain is consistent and you have enough resources to do arithmetic in it, your axioms are never going to generate a complete account of everything that it's provable and true about that domain. So there's always something that's going to be left. That incompleteness is inherent, right? If you can live with that, then welcome to the club. Right? I think actually that makes mathematics more interesting, right? And more alive and full of unexpected discoveries. So I'm all for that, right? And I'm trying to say that yes, that's exactly what happens, right? As you go beyond arithmetic, right? So understanding a concept and formulating in a particular language are related things, but distinct, right? Given that understanding of numerical concept is prior to the axiomatization of the relevant theories that invoke these concepts, right? Typically, it's not by chance that we had a lot of practice doing arithmetical operations before axioms of arithmetic were ever devised. There are a lot of practice dealing with complex numbers before any axioms for complex number were ever devised, right? So there is a practice of some understanding of some concepts that guide the axiomatization, not the other way around. And of course, the process of axiomatization, it's important. It would be silly to deny that, right? And often concepts are refined as a result of axiomatization, right? Often they are distorted, right? So you have to be careful. Sometimes you end up with something quite different from what you're trying to do, right? So for example, when Abraham Robinson introduced non-standard analysis, right? Exploring non-standard models of analysis. And he said, oh, those some of those non-standard numbers are positive, but smaller than any number, are exactly the infinitesimals that Leibniz was trying to articulate. And then Robinson said, now we have a revival of Leibniz infinitesimals in the 20th century. I think even though this is very suggestive, it's highly misleading, right? Because the concepts that you are invoking in order to create the non-standard models, the kind of saturation principles, the third order level that it's required for each of the models of non-standard analysis, the compactness theorem that is required to underpin this whole construction, all of that couldn't be more foreign to the Leibnizian understanding of infinitesimals. So I think it should do a serious historical reinterpretation to try to squeeze in a particular axiomatization into a prior understanding of infinitesimals. Okay, so that's a warning, right? And I'm not saying that we should not axiomatize. Of course, that we should. Non-standard analysis would not be possible without axiomatization. And so I think it's important, but we need to understand the limits, right? And when it's appropriate to apply the axiomatic tools and when it's not. Okay, now, one of the responses that early on people had to these results was, all right, yes, we can see that the Gödelian sentence, this sentence is not provable, is true, it's arithmetical, but it's highly artificial, right? So let's just ignore it, right? So, because this is something that just, logicians could, think of, and so mathematicians just say, well, we'll live without it, right? Well, that's not a good response, right? It turns out that there are perfectly good mathematically statable statements, right, with mathematical content that cannot be proved in the relevant system, right? And so you cannot just dismiss the incompleteness, the Gödelian incompleteness, as just an artifact of a certain formal understanding of mathematics. That would be, I think, inadequate as well. So we shouldn't go into the opposite response, which is just ignore the result, right? I'll give you a couple examples to illustrate, right? One in sort of analysis, the other in set theory. So suppose that S is a Borel set, right? We have a topological space, right, that can obtain from open sets through operations of countable union, countable intersection, and relative complement. So we have a set like that. Now, in this case, there is a Borel function f such that the graph of this function is either included in or is disjoint from the set. Now, you may say, look, this seems sort of easily statable theorem, right? Shouldn't we be able to prove that from, piano arithmetic, for example, right? Second order piano arithmetic is all you need to do analysis, right? So in principle, we should have been able to do that. Well, it turns out Harvey Friedman, in a beautiful result, established that you cannot prove this in full second order arithmetic. So this is a result statable in the language of analysis, right? Second order piano arithmetic. That's the language you need to do all real analysis that mathematicians do, but they cannot prove that in that language. That was one of his results, right? In order to prove a result like that, you need to invoke full Zermelo-Fraenkel set theory, right? So you go way beyond what is expressible in a just second order arithmetic, right? That's an example of a straightforward mathematical claim that cannot be proved out of, in this case, second order piano arithmetic, right? Now, you can prove in a much stronger mathematical framework, ZFC, right? But of course, if you're interested in analysis, presumably you're interested in what can be proved out of assumptions involving second order piano arithmetic, right? So theory goes add a lot of extra stuff, right? And that's what's needed in order to prove that result. Okay, the second example says, well, how about the theory itself, right? So consider the claim that projective sets are Lebesgue measurable, right? So, and it's something that set theorists have been trying to prove for a long time until in the 70s, Solovey proved that actually this result cannot be proved even in ZFC, right? Even though you would expect to be able to prove it there, right? It turns out what you need is something even stronger than ZFC. You need to add a huge, large cardinal. So it's called Woodin cardinal, right? And in that theory, where you can add, this is a theory that it's strong enough so it can prove models of ZFC in it. And that theory can then prove the result, right? So, but of course, then we don't know whether that theory is consistent, right? And then you're always doing some catching up, right? So the idea is, you may think, oh, okay, I cannot prove the result about the Borel function in pure arithmetic. I can prove in ZFC. Yeah, but I don't know whether ZFC itself is consistent or not. Right? So, well, it does have a consistency proof if you have inaccessible kernels, right, and have models of it. Well, but then you need to have some reason to think that this even more powerful set theory is itself consistent enough. You go to regress. So the worry here is, even though, so I think those are mathematical statements with pure mathematical content in them, they cannot be proved from particular set of axioms, right? So the Gödel phenomenon is a significant one, right? On the other hand, the incompleteness is not something that you can resolve, but just shifting to a more powerful theory, because you just find a different incompleteness as you move further down.
Well, indeed, you are just extending the domain, actually, in mathematics, because if you cannot prove, for instance, this theorem about the Borel set, as you say, this cannot be proven in second-order arithmetic, well, you're extending the domain, and then you can go on. That's
You do,
about it.
and that's how mathematicians operate. Just
Right.
give me more resources so I can
Yeah.
settle the result, right? But that doesn't always work that way, right? So, for example, if you think about results that are independent of ZF, so the continuum hypothesis, right? You can settle those things by extending ZFs in some ways, right? And but also refuting it by extending in different ways. So the question is there a fact of the matter as to what the value is of the continuum hypothesis? Right? So the idea of simply extending the lanes doesn't seem to work in general, right? And of course, even if it worked, the question still arises. The larger theories will have their own incompleteness, right? You're just shifting one incompleteness for another, right? And you're just catching up, right? So I'm going to mention in a moment some strategies to avoid incompleteness, but they have some costs, right? And that's what. Okay, so far my point is, I think incompleteness here is actually a good thing, right? Because those are things that, of course, what they show is limitations of expressive resources of certain languages, right? And how you can establish certain results, right? And what is minimally required to prove certain theorems. So that, in that sense, identifying the incompleteness may actually be heuristically fruitful, right? Because you may not be able to prove the result of the Borel set in second-order and arithmetic. Well, you can prove in ZFC, right? So, but that requires moving up in terms of the kinds of assumptions that you need to be made about the domain. Okay. Now, we can move beyond mathematics and also find inferential incompleteness, right? And in a series of very interesting papers in the 90s, Newton da Costa and Francisco Doria found the Gödelian phenomenon all over the place, right? And so, for example, in classical mechanics, so they show that it's impossible to decide whether a given Hamiltonian can be integrated by quadratures, which leads to a formulation of Gödel's incompleteness theorem for Hamiltonian mechanics. But if you think about classical physics, you formulate the theory mathematically, right? Once you formulate that, what they show is a way in which results about the theory will be undecidable, right? So, of course, undecidability here, it's a form of expressing another kind of incompleteness. Now, about something that it's meant to describe the physical world. They didn't stop with that, right? They consider also dynamic systems and chaotic systems, right? They show that there's no algorithmic procedure to test whether a given dynamical system is chaotic. No wonder it's so hard to prove that certain dynamical systems are indeed chaotic, right? But there's no algorithmic procedure to do that. Right? They also show that given a dynamical system that has an equilibrium point at the origin, one cannot algorithmically decide whether the equilibrium is stable or not. Right? So those are, again, properties of dynamical systems that cannot be decided on the basis of the mathematical framework used to express these properties. Right? But you can even move to the social sciences, in economics. Right? So the incompleteness all over game theory, right? Including an interesting result that for finite games, whose equilibrium cannot be proved to be computable, even finite games, right? So, so that those are interesting and significant results. Again, all of them assume a certain axiomatization of the relevant domains, right? Either you're doing game theory, dynamic systems, classical mechanics, but once you axiomatize them in a certain way, right, there are going to be undecidable statements that provable, so, right, given results emerging from Gödel's theory. Okay. Of course, the inferential completeness depends crucially on the underlying logic, right? If the logic is infinitary, so for example, if it has an omega rule, right, with infinitely many premises, then the Gödel's theorems does not go through. In fact, why? Well, you just think a proof is a finite steps of inferences, right? So that's built into the proof. If you don't have that, the proof doesn't go through, and the theorem doesn't apply. Of course, you need to have a trade-off here is now you have proofs that are infinitely long, right? Right, so that's the trade-off, but you have a system that is complete, right? Another possibility, right? If the logic is very consistent, right? If not everything follows from a contradiction, and the consistency of the theories is no longer assumed, Gödel's theorems also does not go through, right? As you saw, the consistency is a crucial assumption of Gödel's theorem. If you don't have that, the theorem doesn't apply. So again, you may have the completeness of arithmetic.
Otávio, to which results you refer for the last claim? Is that a priest-like stuff or?
Sorry?
The last claim refers to results by priest or?
Oh yeah, no, here, yeah, I'm thinking priest, for example, has his LP is a system in which that goes through, right? So, but the point is, well, it doesn't have to be only on LP, right? All the quantum system logics, you can.
I don't even believe it in LP, but.
Oh, well, we don't have to believe it, right? No, yes. My point is, if you're willing to let consistency go as an assumption, right? The result, the proof of the theorem doesn't go through anymore, right? Because.
But the theorem explicitly has either the system as inconsistent or. So of course the proof still goes through.
No, then if the system is inconsistent, then everything is provable, including the Gödel sentence.
That's
but that's the way, because look, Gödel was not working on a particle system logic, right? So if it's inconsistent, the Gödel sentence is probable. Right? So, but we can talk more about that. Again, I'm not suggesting that, okay, we should all embrace inconsistency, right? I'm just indicating that there are built-in assumptions in Gödel's result. If you question those assumptions, well, then there's no reason to take that incompleteness. But there is a trade-off, right? Then you need either entertain inconsistent theories, right? Or rules that have infinitely many premises, right? So those are the options, right? But there are options, right? So, in a way, I think this should not surprise us, right, us, because what follows or not for certain statements depends on what can or cannot be stated in the language in question. And so first order logic, we all know, is complete. But it's complete in part because it's limited in what it allows us to express. If you allow us to quantify not only over objects, but you quantify over properties of things, then you're allowed to express over things beyond what is allowed for in first order logic. You get a more expressively rich language, but then you can express certain things, recognize that they are true, and you can no longer prove them. And then you get the incompleteness of second order logic. So that kind of trade-off, right? It's a trade-off that we need to decide, right? Between expressiveness and completeness. You may be able to express more, but prove less, right? So, in a way. Okay. So let me say a few things, and I'll go faster here with information completeness, right? Here the idea is focus now on the data, right? On the information about a particular domain rather than what can be inferred from the domain in question, right? Now, it's often the case that we just don't know whether certain results hold or not about a certain domain, right? And the result is the relations that express, relations among the objects that express that are partial, right? They don't give complete information about the domain in question, right? So, and this is something that, Newton Lacoste and Sylvain French, and I've written about it as well, right? So you can think about a domain of objects and a family of relations on these objects, right? A relation would then be partial if it has three components, right? Some objects in the domain are related by the relation in question, right? Are known to be so. Other objects are known not to be so they're not in the relation. But for a lot of those objects, it's just not known whether they are or are not in the relation, right? If that happens, then that's a partial relation, right? It's a relation that encodes the partiality of information about the domain in question. And you have a corresponding notion of structure, right? That will be partial, provided that the relations over the objects in that structure are partial, right? So you can think about a partial structure as a way of encoding information about a domain partially, right? It doesn't include every bit of information about that you might be interested in. Okay, I'll give you just a quick examples, even in perfectly standard science. Now, I'll move to biology, an example I like a lot, right? So this is a micrograph that you found in the work of George Palade in the mid-50s, right? He was using a transmission electron microscope, right? And he was scanning cells, right? Of course, there's a long-standing practice of biologists by that time of using microscopes to look at optical microscopes to look at cells. He used an electron microscope. And you notice that you have this nucleus here as you would, and the membranes as you would with an optical microscope. But near the membranes, you found that there are those little dots, right? And he literally had no idea what is it that he was seeing, right? So he thought, well, maybe this is an artifact of the method of preparation. So he changed those things, and the little dots were there. Or maybe that depends on the source of the organ in the body where the cells were collected. You change those things, the cells were there. Maybe this depends on the animal, right? And change those things, and the little dots were there. So it looks like, oh, this is a genuine feature of the cell that was unseen, right, before. So what he did, he triangulated, he ultracentrifuged the sample with the cell, and he expects to have different segmentation times. And that's exactly what happened, consistently with the measured size of these particles. Still, he had no idea what is it that he was seeing, right? He gave the paper the least committal title possible, small particulate component of the cytoplasm, because that's the only thing he was seeing. He says, well, we don't know what is it that these particulate components are made of. He conjectured that they're mostly made out of acid, but he didn't know. Right? And then 2 years after the publication of this paper, additional chemical analysis was made, and it was indeed, the particles were mostly ribonucleic acid, right? And they're called ribosomes. Now, what's interesting here was looking at this images of that sort, that the biological community convinced itself that ribosomes exist. Now, a lot of information was completely open, right? Even by the time in which the paper was published, what the function is of these particles. What are they made of? Do they have a linear structure? How they are related to other components of the cell? Why are they in the membranes, primarily? And a lot of things were just unknown, even though we recognize that there is this new object. Right? I give this as an example of the impartiality of information that is crucial in scientific research. And of course, that partiality is what propelled additional research in molecular biology. Right? And biologists try to answer those questions, and then they discover that this the ribosomes are crucial in synthesis, protein synthesis. They have all kinds of additional structures and so on. And as additional information is found, other questions are left over, right? And so the partiality just shifts, right? And in that sense, it's similar to what happens in mathematical case, right? You may be able to settle some result, making some assumptions, but when you make those assumptions, other things are left assumed, bringing additional incompleteness. Okay. So I have another related example. I'm going to skip for the interest of time. Let me just say a few things about semantic incompleteness, right? So this is incompleteness involving the referential devices of a language, right? How is it that we are able to refer to certain things using linguistic devices, right? And what are the limitations? What happens is it's often indeterminate, right? What the reference of certain terms ultimately are, right? Famous case, right? That when we're considering the shift to relativistic physics, right? So we have now two concepts of mass. One concept that does not depend on the speed of the object, that's Newtonian mass. One that does, that's relativistic mass. So when we're referring to mass, what is it that we are referring to? Relativistic mass or Newtonian mass, right? They are different things, but they are also related, right, in interesting ways. So how can you determine that reference, right? Without, of course, losing sight of the differences between Newtonian physics and relativistic physics. Of course, people all too quickly say, oh, we can always derive the results, Newtonian results from relativistic ones by just constraining, ignoring the closeness of speed of light, closeness to light, closeness to huge gravitational fields, and then we just get the results from relativistic physics of Newtonian physics. The trouble there is, even though you may get the same mathematical results, they mean something quite different, because you have fundamentally different conceptions of mass. One changes in speed, the other doesn't. And that makes a whole lot of difference, right, in terms of what is it that you're capturing when you're trying to preserve from one theory to the other. Just preserving the mathematics is not enough, right? You need to get some of the content of the theory. But when you get to the content of the theory, you get exactly the kind of referential indeterminacy that we're talking about. Right? And then you're back to that form of incompleteness. The concept of mass is such that it doesn't uniquely refer to Newtonian mass and relativistic mass. Okay, so that's one example. Another example of course, different but related is the very concept of vagueness, right? Vague concepts, right? That have their own kind of referential indeterminacy, right? So suppose we are studying, all right. Here we're supposed to have an image of a color spectrum, not this X. All right. So now you have to imagine a column spectrum. Right? So here, right, from red to yellow, right? So as you go down the road, right, each small shift from a hue from one hue of say red to the next one, they look indistinguishable, right? And as you, this is indistinguishable from that, this and this. And as you go down, they look indistinguishable until you get to yellow. And they say, well, right, something went wrong. Because obviously, the yellow is different from the red that we saw, right? This is exactly the phenomenon of vagueness, right? Where small incremental differences don't make a difference. But over extended repetitions, they do, right? That opens up Sorites paradoxes, right? So you can prove that everything's red using exactly this column spectrum. Of course it's not, but that's what it follows. So the question there is this: our color concepts, right, are such that they allow for that kind of vagueness, right? I want to say that kind of vagueness is a form of incompleteness, right? Because the concepts are such that they do not uniquely pin down exactly what it is that we are referring to when we refer to something being red. Because they allow for this, is this red or not? Again, it's part of being a vague concept that certain things are definitely red, certain things definitely not red, but it's not determined for certain things whether they are definitely red or not. And that's exactly the expression of the inherent incompleteness, right, of those concepts. Okay. So, as I just mentioned, certain phenomena cannot but be incomplete. Color concepts is one, but there are others, right? Some, of course, are not directly connected to the sciences. Think about fictional objects. Sherlock Holmes, right? What's the color of the socks that Sherlock Holmes was wearing when he was killed by Moriarty? Nothing in the novel specifies that, right? You can say maybe there's no fact of the matter about that issue. So that's inherently incomplete. Now, I actually think that it's part of what it is for something to be a fictional object, right? So be always, even if you say the author of the novel says all the descriptions here are complete. Sorry, that doesn't make it so, right? And then there will be things that are just undetermined, right? Now I may say, okay, that's fiction, right? So okay, we can live with this incompleteness in fiction, but how about science? Well, I want to say that the same thing happens in the sciences, right? Think about some non-denoting terms, right? When you get to the perihelion of Mercury, the astronomers are trying to find out, okay, why is it that Mercury gets so much closer to this dark in the orbit when it gets closer to the sun, right? Of course, they learned their lesson with the discovery of Neptune, right, which was basically discovery of calculations from Newtonian physics. So they said, well, we'll do the same thing here. There's a new planet, right? Of course, they also posited that maybe the mass of Venus is larger than we thought, and that's what's interfering, but there's no empirical reason to think that that's going on. So they posit this new planet. It turns out that the planet doesn't exist, right? And but we're referring to them nonetheless, right? And the fact that you're referring to them requires us to accommodate talk of these kinds of referential indeterminacies. And more generally, then I want to say, whenever you invoking scientific idealization, so for example, you think that the Earth is just a perfect sphere, right? We know that it's not, but it's too damn complicated to consider it for the shape it is, right? You're actually now introducing also some incompleteness, right? So for example, you're introducing an incompleteness about the actual shape of the Earth, right? You have a little model that you can get results out of a simplified account. But if you're interested in talking to you about the Earth rather than an abstract counterpart of it, well, you have now an incompleteness in place. So this phenomenon are inherently incomplete. To wrap up, some of the incompleteness I've been talking about is epistemic. Some of them comes from our lack of knowledge and information about the domain. Others might be inherent in the objects themselves, right? So that it's an incompleteness as a feature of the phenomenon, of the world broadly understood. But however we think of that, I think incompleteness clearly has an heuristic role, right? The fact that we recognize that incompleteness opens up new avenues for discovery. And that's an important trait, right? We learn important lessons from those incompleteness. So even if we cannot ever completely get rid of the incompleteness, we gain something out of the engagement from the serious attention to them. So, to conclude, I think as opposed to inaccuracy, empirical inadequacy, and irrelevance, which typically should be corrected if we can, incompleteness is a pervasive trait of scientific activity in ordinary life. It can be accommodated by suitable partial structures that encode partial information about the relevant domains, and it often suggests new avenues of research. And this, I think, is a very significant trait for incompleteness and why it's here to stay. Thank you very much.
So we have some minutes for discussion. Maria, there.
Hi, I was wondering if you have talked about the possible relation between incompleteness in the sense of epistemic ignorance and the tolerance of other defects in science. As it seems to me, at least in the literature of inconsistency toleration, it is often related to the fact that we don't know yet, for instance, which of the conjuncts of the contradiction is false, at least or are also. And I was wondering if you have any thoughts on that.
I fully agree with you. I think, yeah, I think you can say similar things to inconsistency, right? In the sense that they point to maybe consistent successors, right? They indicate some tension, some trouble that we need to identify. In that sense, of course, they have an heuristic role, right? And which is significant, right? Some people, of course, think that they're the whole truth, right? If you're the atheist, you think, okay, some of those inconsistencies are there because they really capture the way things are. I'm agnostic about that side. I don't know if there are true contradictions or not, right? But I do think that inconsistencies are significant, right? And in all kinds of ways, right? So they're all, even if you consider contemporary science, right? The kinds of ways of dealing with infinities in quantum field theories raise all kinds of concerns along those lines, right? About how to accommodate what's going on, right? And so wonder that physicists look for different frameworks, right? If they can improve on those results. So yeah, I agree.
Okay, Ioannis?
Yeah. So at some point when you were talking about semantic incompleteness, you talked about the case where you might be able to derive from the newer theory, in some limit form, derive the older results, right? And you said preserving the mathematics is not enough. You need to get the content preserved. And I just wonder exactly how you draw this distinction, because of course here we're not talking about preserving the mathematics as in only the structural form of the equations, but also the values. Right? You're actually deriving something more concrete than merely so it's not just the old structural realist objection. Right? So is this merely the distinction between extension and intention? And why should we care about the intention in science?
Right. No, I don't think it's it's that distinction. I think the content there is just that, as you correctly noted, we're trying to use the mathematics to describe some piece of the world. Of course, the mathematics per se doesn't describe anything about the world, except perhaps for cardinality considerations. So you need to interpret the mathematics. So you need to say, look, those functions that you are introducing here in your equations refer for these kinds of things. And it's that which flashes out the content of the physical theory informed by the mathematics. But once you do that, then you no longer can bypass the interpretation of mass. Are we talking about relativistic mass or Newtonian mass? Because then it's part of that content, whether or not these mass change with speed or not. Right?
But there is something common to the interpretation, namely, we can use the same techniques to make these measurements, and they're affecting systems in the same way, right? If we launch rockets, for example, we need to take into account these kinds of issues. You can either do the relativistic calculations or you can do the Newtonian ones. The relativistic ones are better, but still, we're connecting with the same world in a sense, right? So I can't see how these things are completely separate.
Well, the question, yeah.
And so going back to the point you were making, I can't see how by preserving this maths in this more concrete way, not just the structural unit way, let's say, you're not also preserving some content.
No, you are preserving some content. The question is, what is the content that you are preserving? Right? That's where the indeterminacy is. Because you cannot say, look, I'm preserving mass. Because mass is not referentially determined. You can say, I'm preserving relativistic mass. But then you just refuted Newtonian physics. Right? The theory is just plainly false. And then the idea that you are preserving needs to be treated with care, because in fact what you're doing is you're ruling out a theory that is wrong and putting something quite different in its place, even though you can account for the same phenomenon.
Okay, so I guess your main point is basically the indeterminacy point,
yes.
Right? But so I think the way you phrased it was a bit too strong when you said no content is preserved. Because the way I understand indeterminacy also is, it's not as if anything goes with indeterminacy, right?
Sure,
it's just that some things
yeah.
are not fixed. That's
right.
what it's saying, right?
That's right.
So if you formulated this in terms of content, you would say some of the content is not fixed, right? But so in fact, the kinds of examples that Quine, for example, gives are precisely examples where it's not that anything goes, it's just that some things cannot be fully fixed.
That's right.
Which means that others, of course, are.
No. The point is not, we don't know when we're talking about chairs or tables. And no, of course, there are a lot of things that are fixed, assuming a